Welcome to Echocardiography lecture series. Left ventricle size and function assessment is very important. Having the knowledge is essential, however, training the eyes is as important. This is achieved by reviewing hundreds and hundreds of echocardiography studies. So let's begin. Welcome to left side chamber quantification part 1, where we're going to discuss LV size and its assessment, LV segmentation and wall motion analysis, as well as LV systolic function assessment. As was mentioned in previous lectures, linear measurements can be done in various ways. We have to understand that usually any structure in echocardiography will have a little bit of bright edges. And when you come and you want to measure those structures, you need to understand from where you're going to measure it. Are you going to include the edges or not? For example, let's assume like this is a cavity here, and this is the edge. Let's say this is aorta, and this is the wall, and this here another wall. So we have many ways to measure a cavity or a tissue. It is either from outer edge here all the way to the outer edge, okay, or from outer edge to inner edge, and we call it leading edge to leading edge, or from inner edge here to inner edge. So we have A and B and C. Usually, if you're measuring the aorta, anything distal to aortic valve, like aortic root, ascending aorta, will be measured in leading edge to leading edge convention. If you're measuring a cavity, you will measure it in inner edge to inner edge convention, like here in B. If you're measuring a tissue, you will measure it from outer edge to outer edge, like A. Determining the left ventricular size is a very essential part of echo reporting. In order to say if this LV is normal size or dilated, we have to measure it. And we can do that in either a linear way of measurement or by measuring the volume. Linear way, we can either do it with 2D measurement or by M-mode measurement. Volume measurement, on the other hand, we will measure volume, and it is done either by area length method or equation or the method of disk, which is the most accurate way to do it. Okay, we'll start with the LV size measurement by the linear method. And the one you see here is you're measuring the LV size by 2D linear method. This is 2D and this is 2D. It's not by M mode. And this is more accurate than M mode because in M mode, some of the machines you cannot really choose the angle. The angle is determined by the position of the probe. It has to start from the probe, either go this way, then this way, and this way. So you cannot measure it this way. And this is not accurate. However, some vendors, you can do something called anatomical M mode, that you put an M mode after you obtain the 2D. Anyways, so 2D is more accurate than M mode in this situation. How to measure the LV size? First of all, you need to measure the LV at end of diastole. It is not important exactly end of diastole, mid of diastole. The most important is you have to go frame by frame and choose the frame that has the largest LV size, the largest LV cavity, and you freeze there and you measure. And how to measure it? You measure it at this level, the level just distal to the tips of mitral valve, here exactly. And this dotted line here This is the axis of the LV. So you have to measure it in an angle perpendicular to the long axis of the LV. Exactly the same way we see it here. So in diastole, we measure the septum. In diastole, we measure the LV internal dimension in diastole here. And then we measure also the posterior wall in diastole. So it's LV posterior wall in diastole. In systole, on the other hand, we need only to measure the LV internal dimension in systole, and this is just to include it in some of the other calculations. We will come and see it in the coming slides. This is the M mode, and you can also do the measurements here. After you obtain an M mode, you do your measurement. This is the diastolic septum, and this is LVIDD, and this is the posterior wall, and this is the systolic frame here, systolic LV cavity size here. It is common in elderly patient to see something called sigmoid septum or an S-shaped septum, like the one here. It comes like this and this. So it has a bulge here in the proximal part of the septum. In this case, like we see it here in the video, in this case, you should not measure the sigmoid septum. You should measure distal or after the sigmoid septum, like here. So you don't measure this part here. No, you should measure just after this part to be more accurate. And this is a reference values of the LV size. So if LV size, LV, let's say LVIDD is within normal, we call it normal. We have for males and for females different numbers. And also we have ranges for mildly dilated, moderately dilated, and severely dilated. It is recommended always to index it to the body surface area. So anything, any number we like to index it to body surface area, we have first to get the body surface area by calculating it from height and weight. And then we divide anything over the body surface area. So let's say if it is 4, the LVIDD, and the body surface area is 2. So the indexed LVIDD is 4 over 2. It is 2 centimeters. If it is in centimeter, it will be 2 over meter square. So this is the index size. And then we decide if it is dilated or not. Historically, LV volume were calculated from linear measurements based on assumption of a fixed geometric shape of the LV, like a sphere shape or bullet shape. This is inaccurate, and it is no longer used, like the Tycho's method, etc. It is no longer used. Now, in order to get the volume of the LV, we have either the area length method, which we see it here, or the method of disk, which we will see in the coming slides. In area length method, there is an assumption of a bullet shape of the LV still, so it is not the best because still it assumes a fixed geometric shape of the LV. However, it is better than calculating from only linear measurements. How to do it? This is the equation here. We need to get the area. This is the area. We measure it in short axis at the level of mid LV here, where you see the pap muscle. So you measure the cavity here, you measure this area, you trace it, and you get the area. Then we measure the length of the LV from insertion of mitral valve to insertion. So this is the annulus of the mitral valve. So from the annulus going all the way to the apex here, exclude all trabeculation, and we calculate the volume. Volume is 5 times area times length divided by 6, and it will come in ml. A better way to calculate the LV size and LV volume is by method of disk. So in this method, the LV is cut into small disks, and we measure the volume of each disk separately, then we add them all together. It is very simple, and it is done in two plane to make it even more accurate. It is not only one plane like the area length method. No, it is done in two plane, where now you have a 4-chamber and 2-chamber measurement. So you measure each disk in 4-chamber and 2-chamber. Now we have 2 dimension of each disk, dimension 1 and dimension 2, and also we have the height. So we measure the volume of each disk, and the volume of each disk is pi times dimension 1 times dimension 2 times the height, and we will get the volume in ml. And then we add up all those volumes, and we call it MOD, or method of disk, or modified Simpson way. Many times there will be an error in tracing the LV. Accurate tracing, of course, you should avoid foreshortening and choose the correct frame. For end diastolic frame, choose the frame that has the largest LV. End systolic frame, choose the frame that has the smallest LV. So after you choose the frame, just freeze and start your tracing. Tracing should exclude trabeculation. It should be done where in the area between the compacted myocardium and the non-compacted myocardium. So it is the interface between the compact myocardium border and LV cavity. So those all are trabeculation here. We should exclude those trabeculation and just measure the compacted area. So a correct measurement should be as follows. Start the measurement something like this. This is how you trace. Similar to 2D dimension, also in volume we have reference values, and we have to index it to get a more accurate estimation of the size. "3D LV volume is the best if you can do it. It has the advantage over 2D that foreshortening by itself is less relevant, because you have the full volume and you can cut it a different way, and usually it is more reproducible because it is less operator dependent, because also the tracing will happen in automated way, and you can adjust the tracing, but usually it is automated or semi-automated way. The only thing you need is to optimize 2D resolution and temporal resolution, and make sure before you proceed to measure your 3D measurement, you need to have a good 2D. So a good 2D image with good border is a prerequisite to have a good 3D. So if your 2D image is bad to start with, don't waste your time and proceed with 3D. So 3D volume measurements has a reference range. However, it is not well established like the volume we get from 2D. Now proceeding to LV mass. In order to say that this ventricle has a hypertrophy or it is hypertrophied, we need to calculate LV mass. Not like previously done, we only measure the wall thickness. Now, wall thickness by itself, if we measure and we think that this wall is thick, we cannot say hypertrophy. We need to measure the LV mass, and this is in every echocardiography or transthoracic echocardiography study. How we measure LV mass? The commonest and easiest way to do it is linear method, and it is very well established, and it is still done. 2D method, we can do it. It is a little bit time consuming. And finally, the 3D method, which again, it is not widely available. So as just mentioned, the linear method to calculate the mass is very well validated and extensively studied and easy to perform. The formula for LV mass is this. We call it the Devereaux formula. So what we need to measure is the ventricle, the septum in diastole, LVIDD, the LV internal dimension, and diastole, and posterior wall and diastole. So this is what we need to measure, and the mass in grams will be calculated automatically. The LV mass in 2D method is a little bit complicated. First, you need to measure two areas in short axis. Area number 1 here, which will include the LV muscles inside. So the cavity and the muscles are included in the circle. And also then we measure only the cavity here. We exclude the muscle. And by subtracting both of them, after we get the volumes, we will get the volume of the muscle by itself. Then we convert it into mass. And this is how we get the LV mass by area length method. This is also the 3D method. Similar to the volume, everything will be done automatically. The tracing of the endocardium and epicardium will be done automatically. However, it is allowed to do some manual adjustment here and there wherever you think it is necessary. The reference value of 3D mass is not yet endorsed, so it is not yet recommended because we don't have a quite validated mass reference values. Again, similar to any measurement, we have to index it to the body surface area, and we have a difference between males and females. So this is the normal for male, utilizing the linear method, and if it is increased, it is then hypertrophy, either mild, moderate, or severe, and similar thing for female. So again, we have difference between the linear method and the 2D method. 2D method here is the area length method, which we have just seen. Before we understand and digest LV hypertrophy, we need to know the relative wall thickness. So relative wall thickness is the ratio of the muscle thickness of the L to the LV cavity. So instead, here how we calculate it, and instead of measuring posterior wall and the septum, and then we calculate the ratio to the LV cavity, it was initially done by having only the posterior wall here, then we double it, or we multiply it by 2, so as a substituent for the septum here, and then we divide it by the cavity, the LV cavity and diastole, and this is how we get the relative wall thickness, and we need to memorize it very well. So the options for hypertrophy will be dependent on the mass and relative wall thickness. It will be like this. If you have a normal mass and a normal wall thickness, relative wall thickness, a normal relative wall thickness is less or equal 0.42 or 42%. This is the normal relative wall thickness. So if you have a normal mass, normal relative wall thickness, we will call it normal. If you have increased mass, then now you have hypertrophy. And the hypertrophy can be either concentric or eccentric. So again, if the mass is increased, it is hypertrophy. Then, if the relative wall thickness is also increased, so the thickening is happening toward the cavity on the expense of the cavity. So thickening inside, and the cavity is small, so relative wall thickness is high. So this is concentric hypertrophy. And on the other hand, if you have, let's say, dilated ventricle, so the mass will be increased, but the relative wall thickness will be decreased or normal. In this case, you will have something called eccentric hypertrophy to the outside. Eccentric hypertrophy. Again, definition of hypertrophy is increased LV mass. And then, in order to decide if this increased LV mass or this hypertrophy, is it concentric or eccentric, you have to look into the relative wall thickness. If relative wall thickness is increased more than 42%, it is concentric. If it is normal or decreased, it is eccentric. Now proceeding for LV systolic function assessment. There are clues that indirectly can tell us or give us idea about the LV systolic function. One of them is acquired through M mode, and it is M mode through the aortic valve leaflets and the shape of that. So normally the aortic valve leaflets, when they open in M mode, they would have a box shape like this, indicating adequate volume going through the aortic valve. However, if this volume is decreased for any reason, maybe LV systolic dysfunction or maybe mitral regurg, so most of the blood, instead of going antegrade through the aortic valve, it will go the other way through mitral valve in severe mitral regurg. At the end, we will have a decrease in stroke volume. This decrease in stroke volume will not allow the aortic valve to open very well. So you will have this bullet shape aortic valve in M mode. So you can see it opens initially well, but quickly the leaflets start to go down quickly, producing a bullet shape M mode through the aortic valve. Before proceeding to the next M mode clue, we have to understand the different mitral valve waves in M mode. So this is an M mode of the mitral valve, and this line here represents the anterior mitral valve, and this is the posterior mitral valve here with time. So here the mitral valve is closed. In beginning of diastole, the mitral valves or the valve leaflets start to open. The beginning of valve opening, we call it the D point. And then this is the anterior mitral leaflet, will go all the way anterior and open. The peak of this wave, we call it E wave, which is the peak opening of mitral valve. Then the mitral valve leaflets will start to close. Particularly the anterior, we will see it very clear, reaching an F point or partially closed mitral valve. It is not fully closed. Fully closed will be somewhere here, but this is partially closed. and this is due to diastasis. Diastasis is a state of pressure equilibrium between the left atrium and the left ventricle, where there's no much flow going between left atrium and left ventricle. And then when the left atrium contracts, you will have further opening of mitral valve, giving us this A wave. A, atrial contraction. E, early filling. Then C is fully closed mitral leaflets. Sometimes you will have a wave here which is abnormal wave. It is the B wave or B bump. This B bump is due to elevated LA pressure and bad diastolic dysfunction. We will see it in diastolic function lecture. Having said that, there is something called EPSS, which is the E point septal separation. So as we mentioned, this E point here is the peak of anterior mitral leaflet opening, and this is the septum. So it's E point septal separation, the space between the septum and E point. And the bigger is the space, the less transmitral volume. So if you have a bad LV systolic dysfunction, you will have a less volume coming from left atrium to left ventricle. So it is indirect clue, and it is somehow accurate if there is no, again, mitral regurgitation, because if there is severe mitral or significant mitral regurgitation, this one will be overestimated. You will have more volume going through mitral valve to LV, but it does not really represent the true volume that leaves the LV going through aortic valve to systemic circulation. So normal is usually within 6 millimeter. If it is larger than 6 millimeter, usually it represents or indicative of decreased LV stroke volume, again in the absence of significant mitral regurgitation. Another way of measuring LV systolic function is the fractional shortening, and the reason why I'm telling you fractional shortening is you have to know it because it is mentioned, it is history, we should not use it, and it is no longer recommended to use it as a surrogate for LV systolic function because it has a lot of disadvantages. First, let's know how we calculate it. So fractional shortening is the LV dimension in diastole, this one, minus the LV dimension in end systole, this one. So how much did the LV contracts or become smaller divided by the original dimension. So this is fractional shortening of the LV. How much did the LV shorten in systole? If you note why this is inaccurate, because it only represents this part of the LV. Let's assume that this part here is normal and most of your abnormality is mid to apical portion. So this will only misinterpret the LV function depending on only this part and mislead us. So we should not really use it at all. However, normal fractional shortening, since we mentioned, it is 25 to 45%. This is an example of why we should not use fractional shortening, because as you can see here that the shortening in the base of the heart here, the basal segment of the heart, where we measure the fractional shortening, is normal. But look at this part of the heart, the apex of the heart, the mid part of the heart, it is not moving at all. So if you depend on fractional shortening for LV function here, you will say LV function is normal, but actually it is not normal at all. And instead, we have to use LV ejection fraction to estimate LV systolic function, and this is acceptable. Ejection fraction is N diastolic volume minus N systolic volume. So how much is really ejected from the LV divided by the original volume, which is LV N diastolic volume times 100. So it represents the stroke volume. So LV N diastolic volume minus LV N systolic volume is the stroke volume divided by how much volume. So it represents how much ejected from the heart compared to the how much or what is the filling volume of the heart. And the best way to do it, of course, we can do it by a method of disc or area length or 3D. Definitely 3D is the best if we have the capability of doing 3D for the reason mentioned before, followed by biplane method of disc. It has to be biplane. And finally, area length method. But the one that is most commonly used is the biplane method of disc. And again, we have a normal values, different for male and females. For a male, the minimum is 52. For a female is 54. And then you have mild, moderate, and severely reduced. It's not, abnormal ejection fraction is either low ejection fraction, let's say less than 52 for a male, or even increased ejection fraction, which represent hyperdynamic. So if you have it like more than 70% for male or female, it means the LV is hyperdynamic, and there is a reason for that. It cannot be normal. Either it is like post-exercise, or there is anemia, hyperdynamic circulation, or acute mitral regurg. So we have many reasons for hyperdynamic LV. Another parameter of measuring or estimating LV function, being systolic or diastolic, is called MPI, or Myocardial Performance Index, or TI index. It is not commonly used. It is not for everyday use because it is a little bit time consuming. It's mainly used in a research settings or in special situation. However, just to have the picture completed, we have to mention it and explain it. So this is, let's say this is the mitral valve. So this is diastole here. This is the filling of the heart here. So the heart, the LV fills from here to here. And then you have some isovolumic contraction time here. So there is no flow going up or down in this area. Then you have the ejection time, where there is a flow going through the LV, from LV through aortic valve here. This is the ejection time here. And then you have isovolumic relaxation time, beginning of diastole, but there is no filling of the LV. And then again, the LV start to fill through the mitral valve. So what is this MPI, or performance index? It is the ratio of isovolumic time. So the time that there is no actual flow going, there is a work, but this work is without flow. So we add up those isovolumic contraction time plus isovolumic relaxation time divided by the true ejection time, where there's really flow going. How to do it? Either we measure independently the isovolumic contraction time and isovolumic relaxation time, we add them together and then divide it by the ejection time, or we measure something called mitral closure to opening time. So this is mitral closure here to opening time. Subtract from it the ejection time, and then we will get the isovolumic time. And then again, we divide it by the ejection time. So it is the percentage of how much work is usually producing flow from the work that does not produce any flow. And normally it should be less than 40%. So less than 40% of the work time is accepted not to produce any flow, only less. More than 40% is abnormal and indicative of abnormal LV function. And also you have to note something, that since it is not purely systolic, let me show you, because this part here is part of diastole. So the MPI reflects LV function, systolic and diastolic as well. How to measure this MPI? First of all, we need to arrange our Doppler, the PW or the sample volume of PW, somewhere between the mitral here, this is the mitral leaflets, and the aortic leaflets. So we place it somewhere here between them, so we can capture both flow, that inflow and outflow, and we will get something like this. So this is the mitral flow here, and this is the ejection flow through aortic valve here. And then we can do all the calculation and measurement explained earlier. MPI is load dependent. It is dependent on the preload LV filling and the afterload, which is vascular resistant, as well as the systemic blood pressure. dPdt is another parameter that is load independent somehow. It is the rate of increase of the pressure within the LV, and usually it is during the isovolumic contraction period. I will tell you again why is that. First, but we need to know how it's measured. So it is measured from the mitral regurgitation flow. So this is here is MR, mitral regurgitation. So this is a CW over the mitral regurgitation flow in a high sweep velocity. So we need a high sweep velocity in order to measure it accurately with less error. Then we measure the time it required for the MR velocity to increase from 1 meter per second to 3 meter per second. So we need to measure the time, this one, T, that it needs to increase the velocity from 1 to 3. But what we need exactly is the pressure. So we convert it into pressure by Bernoulli equation. So velocity of 1 is 1 times 1 times 4 is 4 millimeter mercury. 2, 3, which is 3 times 3 is 9, times 4 is 36. Okay, millimeter mercury. So we need to know the time it requires to increase the pressure from 4 to 36. So dP is 36 minus 4 is 32 millimeter mercury. We need just to divide it by the time, this T. And then we get the dP dt, or the rate of increase of the pressure in every second. As you note here that, 36 is way below the aortic pressure, particularly the diastolic aortic pressure. In order to open the aortic valve, you need to exceed the pressure in the aorta, at least the diastolic pressure. 36 is way below that. This is why this measurement is really independent of the pressure of the in the aorta, because it is way below the aortic pressure, so it is relatively load independent. And the normal, it should be more than 1200 millimeter mercury per second. If it is below this, it will indicate LV contractile dysfunction. Shifting gear a little bit and going now to analyze the LV wall motion. And so it is regional wall motion analysis of the LV. First of all, we need to understand the walls of LV. We have the 17, or let's say the 16, 17, 18 segment model. We will concentrate, and the standard is the 17 segment model. 16, it will underrepresent the apex. 18 will over-represent the apex. So most of the changes will be here. So 17 is the standard. We'll start from the anterior. So this is the RV here. This is the RV. So if this is the RV, the septum starts here until here. So this one, after the septum here, this is the anterior. This is anterior. And we start from here going counterclockwise. So this is the basal anterior here, number 1. This is anteroseptal, infroseptal, inferior, infrolateral, anterolateral. So this is basal level. Then we do the same in the mid level. Anterior, anteroseptal, infroseptal, inferior, infrolateral, anterolateral. Then we go to the apex. In the 17 segment model, you will have anterior apex, septal apex, inferior part of the apex, and lateral part of the apex, and then this segment number 17, which is the apical cap. In the 16 segment model, you don't have this apical cap. In the 18 segment model, you will have 6 segments of the apex, similar to that of mid-level and basal level. So as you can see, basal level is 6 segment, mid-level is 6, and apical will be 6. But again, now the recommended model is the 17 segment, and it is not only used in echocardiography, but it is also used in SPECT and MRI. This is how LV segmentation is presented in transthoracic echocardiography. So let's take them one by one. In parasternal long axis, this is the anteroseptal, and this wall here is the infrolateral. And then again you have the basal, mid-segment, basal, mid-segment. Going to apical views, this is the apical fourth chamber. So you have the anterolateral and the infroseptum here. In apical 2, you have the anterior and inferior with all levels, basal level, mid level, and apical level. Similar to apical 4 chamber and 3 chamber. You have 3 levels, basal, mid, and apical. In the 3 chamber, you have the anteroseptal here with all levels, and infrolateral wall here with all basal and mid and apical levels. In short axis, again, you have 3 levels. At the basal level or the mitral level here, and again, here it is very important to determine where is the septum. So this is the RV here. So the septum starts from here to here. So this is the septum. Okay, it means that this wall is the anterior wall. So don't do this mistake and say this is the anterior wall. No, this is septum because this is RV. So this is the anterior wall here, and then you start counting. This is the anteroseptal, and then again you have here the inferoseptum, then inferior, infralateral, anterolateral. And we do the same thing exactly with all different levels. Mid-level here, this is mid-level, and this is the apical level. So after knowing each wall, now we need to grade them and to assess the walls individually. And this is done visually, and we call visual assessment of the walls. And we call them either the wall is normal, choose different color, either it is normal or hyperkinetic. It is called the same, normal and hyperkinetic, or it is hypokinetic or tardokinetic. So hypokinetic is if you see a wall, LV wall, compared to the other walls that it has less thickening. So normal, hypokinetic, akinetic, it is not wall motion. Don't look at the wall motion, look at the wall thickening. How much the wall is thickens in systole. And then akinetic, that there is absent or negligible wall thickening. Dyskinetic or aneurysmal, they will be given the same score. This is the new recommendation, which is it is systolic outward bulge. So aneurysm, let's say this is the LV. Let me just throw, this is the LV. During systole, if you have a bulge outward like this, we call it dyskinetic segment. However, if you have it during diastole, bulge like this, which is also persisted during systole, we call it aneurysm. So this is the difference between aneurysm and dyskinetic. Dyskinetic happens only during systole. Aneurysm is outward bulge in systole and in diastole. Of course, we have to see a few examples to understand. So look at this apical three-chamber view. You can see good thickening all over except this part here. So this is basal part of the infralateral wall. So you look, there is no thickening. So it is akinetic. So the basal infralateral segment is akinetic. Let's look at another example. So look carefully here. This is again apical three-chamber here. So this is the anteroseptal part, basal anteroseptal, mid anteroseptal, and apical septum here, and it is akinetic. It is not moving at all compared to this infralateral wall, which is moving. Now this is the anterior, and this is apical two-chamber. So this is anterior, and if you look carefully, anterior, basal anterior here, the thickening is normal. But if you look at the mid wall here, don't look at the motion, look at the thickening, a rate of thickening. You will see it is hypokinetic. It is not normally thickened. And here, the apical anterior here is akinetic. It's not thickening at all. Similarly, apical cap is akinetic. It's not thickening. The inferior part of the apex here is akinetic. It's not thickening. Only this mid part here and basal part is normally thickens. This is a hinge here, this is a hinge. So where you have a mobile or a moving part here and there, and a fixed stationary part here. If you look here in this apical fourth chamber, you will see that there is a moving part here and here also. It's thickened, but here it is not. It is fixed. It indicates ischemic part, and we call it hinge point. So if you see it fixed, so it is fixed here, but it is mobile here and mobile here. Or it thickens apically and basally, but not in the middle. So there is a hinge point and it indicates ischemic segment. Sometimes you will have abnormality everywhere. So in this example, you will have global hypokinesis or hypokinesia everywhere. It can be with regional variation. So all of the walls are abnormally thickening, but there is maybe one wall, one segment contracts better than the other, or one worse. So here is totally akinetic, here is severely hypokinetic. So again, it can be regional as well as it can be global hypokinesis. There is something called pseudo dyskinesis. It is pseudo dyskinesis. It is not true dyskinesis, but it's pseudo. What's the difference? So again, dyskinesis or dyskinetic segment, it's outward bulge during systole. But if you look at this segment, the apical inferior segment, or here the mid inferior segment, you will see, which is this segment here, you will see that this segment during systole or during diastole, it bulges inside. So during systole, you will have a perfect circle like this in systole. But in diastole, it will go inside like this. It indicates pressure from outside the heart, and usually it is the diaphragm pushing this inferior part of the LV. It does not indicate any LV pathology, but it only indicates pressure from outside. This is pseudo dyskinesis. Part of wall motion abnormality is septal motion abnormality due to conduction problem. So conduction problem can be, like in this example, due to paced rhythm. If you look carefully, you'll see a pacing wire here, or can be due to left bundle branch block. All will give almost the same picture. If you look at the septum here, you will find it shaking and giving some abnormal motion, which we will see in a minute. But if you look also carefully, you will know that the thickening is preserved. You don't have any problem in thickening. It's only in the motion and the timing of the motion. So septal motion abnormality in left bundle branch block. Let me explain to you. So in left bundle branch block, if this is the heart, this is the septum here, and you have the conduction fibers of the heart going here and there. Let me draw the left bundle in blue. So you have, this is the left bundle. Okay. And this is the RV here. So this is the RV, this is the LV. And if you have a problem here in this left bundle, you will have a normal activation of the septum here. The septum will be activated normally, followed by the free wall of the RV, because you have a normal right bundle. But this lateral wall of the LV, or inferior wall of the LV, infralateral wall of the LV, the conduction will be through cell to cell conduction, which is slow. It means that this part of the LV will be activated late. So let's see what happens in M mode. So we have a better timing. First, you have here, number one, you have the septum, septal thickening here. So you can look, it's thickened and it moves towards the LV cavity. This is number one. Then number two, now you have RV thickening. Look at this arrow here, arrowhead. You have the RV thickening, but now the septum will be pulled up with the RV when the RV contracts, because this it is unopposed by any contraction of the LV. There is no contraction of the rest of the LV. Okay, so it will be pulled up, and we call this area, the septum going down and up, septal flash. So it is septal flash. We see it in left bundle branch block. And then it will go back here to normal when you have the lateral wall, the infralateral wall here comes very late, and then the septum will come down here. Okay, so this is what you see it in left bundle branch block. The most important thing here, in order to say that there is ischemia or abnormal wall, you have to look at thickening of the walls. Is it thickened? See the thickness here, thickness here. So it is thickening. So you don't have any ischemic problem in this wall. It's only conduction abnormality due to electrical problem. Now we have another type of septal motion abnormality, which is RV pressure and volume overload. So this is the septum here. Let me draw it in short axis. Let me just okay. So this is the RV here. This is LV. And this is the septum. So the septum, the motion of the septum is dependent on the pressure difference on the two sides of the septum. So if the pressure here in the LV is higher than the pressure in the RV, you will have it bulging toward the RV. Sorry. Yeah. If the pressure in the RV is higher than the pressure in the LV, you will have the septum bulging the other way. It will be flattened like this. This is how it will look. It will be flattened. This pressure changes between RV and LV can be in systole or in diastole or in both. So now we need to see a few examples in order to understand this very well. In this example of pressure overload, you will know that there is a septal flattening. The septum here flattens mainly during systole and particularly end of systole. This is when you have RV pressure overload. So the pressure in the RV exceeds that pressure of the LV, and usually this happens in pulmonary hypertension for any reason, particularly toward the end of systole here. And if you have RV diastolic dysfunction where the RV diastolic pressure exceeds that of LV, you will have it both in end systole, septal flattening, as well as an end of diastole septal flattening here. On the other hand, in pure volume overload, like in severe tricuspid regurgitation, severe pulmonic valve regurgitation, or ASD, where you have a volume problem, you will have this septal flattening during diastole only. If you look carefully with trained eye here, you will see that during systole you will have a perfect circle of this LV. But during diastole, you will have this flattened septum. This is indicative of RV volume overload. So the pressure increases during diastole. It will increase in RV more than that of LV. So in diastole, you will see this septum here flattens, and end of systole, It is almost a normal circle. Thank you for watching. This is the end of part 1 lecture of left side chamber quantification. Next talk will be part 2 of left side chamber quantification.